This video is part of the book Statistical Modeling with R that I wrote and was published by Oxford University Press in 2023. Today I'm going to talk about GLMs and the relationship between these models and the old-fashioned log linear analysis. Starting as usual with exploratory data analysis, frequencies, and then Bayesian model fitting, and the data and codes to run this analysis can be found in the website shown on the screen. Log linear or frequency analysis aim to assess the interactive effects of categorical explanatory variables. So here the response variable is a count or a frequency, and the response variables are all categorical explanatory variables. So this is exactly the same goal as a factorial analysis of variance, only that in the latter, the response variable is not a count, but it has a normal distribution. The old-fashioned approach of contingency tables that at least I learned aim to evaluate the statistical significance of the independence or lack thereof of two or more dimensions, that is, two or more variables of frequency tables. This was in total disregard of parameter estimation. The only thing that mattered uncounted was to assess whether the rows, that is one variable, the effect of one variable was independent of columns, the other explanatory variables in a frequency table of two entries in this example that I'm mentioning. So if you never learned about log linear analysis, all the better for you, because the GLM framework allows to make a more meaningful analysis, allowing parameter estimation and a more meaningful inference that also involves assessing how the model correctly fits or not the data. So we'll take advantage of an unbalanced data set, a data set by Tom Schoner, an ecologist, drawn in the 1970s, to illustrate some ideas of model selection that was the subject of a previous video and a specific chapter of the book. So the goal of the analysis is to determine the interactive effects of categorical explanatory variables on the habitat use of two lizard species in the Bahamas. So here I import the data. The response variable is n, the counts, and so here are the explanatory variables: sun with two levels sun and shade, height with two levels high and low, perch, time, it's the afternoon when the observation was made, and the observations were made, and the two species Grahami and Opalinus, two anolis lizard species. So the question of whether these explanatory variables are related can be addressed with a specific type of plots called the mosaic plots that look threatening at first sight, but can actually be pretty handy. So let's focus on the first graph A. So here we have the two-way combinations of Grahami shade, Opalinus shade, Grahami sun, and Opalinus sun, two explanatory variables, and height, low and high, perching sites. And what we have here in the table is an area that is proportional to the counts. If there were no interactive effects of this combination of the two explanatory variables and the third variable, the areas of these four squares, 1, 2, 3, and 4, would be exactly identical, and they are not, suggesting that there is interaction between some of these explanatory variables. Likewise, we could interpret the rest of the plots, and there is too much information here to be used. So what we are going to do then is to focus on the probability distributions that could be used to model the response variable. So we are going to use the cumulative distribution functions and the QQ plots to assess the two distributions, the Poisson and the negative binomials, that can be used to model the count of lizards. So here are the CDF and the QQ plots, and by far the negative binomial distribution is the most appropriate distribution to model this data. So the response variable n, the number of lizards counted, has a negative binomial distribution whose parameters is a mean and the dispersion parameter phi. So in a completely exploratory mode, I'm going to consider all single effects of the categorical explanatory variables, all pairwise interactions of them, and all triple interactions of them. This is in a completely exploratory fashion of analysis. So the frequentist model fitting, we're going to fit this initial model with the negative binomial distribution, and this hat and a 3 here is a shorthand for including the single effects of each explanatory variables, the pairwise or second order interactions, and the third order interactions between them. So what results is the summary of this model is contains a very large number of estimated parameters, some of which are statistically significant, some of which are not. The model has no relevant amount of overdispersion, which is pretty good. So we are not going to interpret all these parameter values because we are going to simplify this model, and in order to orient ourselves for the process of model simplification, which would lead to a model selection exercise, we are going to obtain the analysis of deviance table that show us the sequential addition of terms to the model from a model with no explanatory variables, then the single effects of all the explanatory variables, then the pairwise interactions and the triple interactions of all the explanatory variables. The p-values here simply show whether the sequential addition of explanatory variables or terms lead to a statistically significant decrease of deviance. So here are the single effects, the pairwise, the second order interactions, and the third order interactions in the analysis of deviance table and in the summary table showing the parameter estimates. So in an exploratory mode, we must pursue to obtain the most parsimonious model can be fit to the data by simplification. This simplification of the initial model, list 1, must always start by simplifying the term of the highest order, in this case the third order interactions, and proceed downwards step by step. It is very important to be systematic in this process of model simplification. So what I did is that I used Lisa 1 as the starting point and generated the specific model Lisa 1.1, in which I deleted a specific third order interaction, the interaction between species, sun, and height, to generate the model Lisa 1.1, that is a special case of Lisa 1 without this interaction. Then I compare these two with the likelihood ratio test. This is the Wilks test, using the command ANOVA that compares the difference of deviance between two models that are part of a nested hierarchy. Then I generated the model Lisa 1.2, which is a special case of Lisa 1 without this other third order interaction. Then I compare the original model with the descendant model, that is a special case of the former, with the Wilks test, and I proceeded likewise for the 10 third order interactions by comparing each model, that is a special case of Lisa 1, with the descendant model. So it turns out, I'm not showing it here, but you can see it in the book, that none of these, the comparisons of none of these models from Lisa 1.1 to Lisa 1.2 were significantly different from the parent model Lisa 1, and therefore none of the third order interactions need to be retained. So we must now proceed. We are now in a state in which we have a model with the only second order interactions, which is now going to be the stepping stone for the next step of model simplification. So here is Lisa 2 is a model with only single level effects and second order or pairwise interactions. So here is the analysis of deviance table. We have the single level effect, the single effects of the categorical explanatory variables and the interactions, some of which are statistically significant, some of which are not. So we will now generate a set of descendant models that will be special cases of this parent model LISA2 in this case without one of each of these second order interactions, and compare them, the descendant models, with LISA2 using the log likelihood ratio test. So here are the models. LISA 2.1, which is a special case of LISA without this second order interaction, and the comparison with the parent model, and I did likewise for all 10 second order interactions. So the final model contains the following terms. The following terms are the single level effects of all categorical explanatory variables and 1, 2, 3, 4, 5, and 6 second order interactions. So it is very important to proceed in this systematic manner. This is called the principle for the model simplification. This is particularly so in unbalanced data set, as it is the case of the one which that we are analyzing currently. So this is the resulting model. This is the resulting model that again shows no relevant overdispersion, meaning that the model is adequately, the fitted model is adequately modeling the variation in the data. So here now we are going to start interpreting these parameter estimates. So LISA3, the current model, doesn't contain third order interactions. It only contains 6 second order interactions. Therefore, we can interpret each of them separately in order to make sense of the parameter estimates. So the reference level for each categorical explanatory variable are the following: Grahami, shade for the categorical variable sun, height, high for the height, broad for the perch, and morning for the time. These were all selected on an arbitrary basis by R using an alphabetical criterion. So in all these models, the intercept is the log of the mean of the response variable for each of these reference levels. So let's look again at the parameter estimates and focus on just one of the second order pairwise or second order interactions, which is the species perch interaction. So the species perch interaction, here I'm showing a 2 by 2 table in which we have in yellow the reference levels of these two categorical explanatory variables. This corresponds to the intercept. This is a log of the mean of the response variable for the intercept. If I keep the reference level for the species unchanged from broad to narrow, I must add this coefficient 0.306. If I keep the reference level of perch, which is broad, and I change species, I must add the special differential, which is 1.333. And if I now change from the combinations of reference levels, Grahami and broad, to narrow, I must add these two coefficients and the interaction, which is here. So after adding and inverting the link function, what we have here is the predicted values of the mean for the 2 by 2 combinations of each of these explanatory variables. What we see here, if we make the ratio, for instance, of Opalinus over Grahami, we see that Opalinus is 3.77 times more abundant than Grahami when the perch is broad, but the difference in abundance by dividing 5.47 by 3 is only 1.82. So this difference in magnitude by comparing the two species in the broad and narrow perching size is what we mean by interaction, that the magnitude of this difference changes depending on the level of the perch explanatory variables. Likewise, we could make a similar comparison by just comparing the preference of each species for narrow versus broad, or broad versus narrow for each of the two species. So we can assess the goodness. So likewise could be interpreted all the remaining 5 pairwise interactions. So it's very instructive to make these 2x2 tables that I just highlighted. To assess the goodness of fit of this model to the data, we use the package room as usual, and then we obtain the Donald-Smith residuals with the package Dharma. These residuals are converted to a normal distribution, and the resulting residuals will only have, again I stress, a normal distribution if the model fits well to the data. What I show here is 6 plots, the residuals against the fitted values. We don't see any relevant pattern here in this graph, which is a sign that the model has a good fit to the data. And when we compare the combinations of species sun in the 2x2 combinations, or the time of the day and sun, which gives 6 combinations, or the species and the perching site, we see that the median of the residuals are all very similar, close to 0, and the span of the variation, as indicated by the width of the box of these box plots, is not too dissimilar between all these combinations of explanatory variables for each of these B, C, and D plots. We see that the converted Donald-Smith residuals do indeed have a normal distribution, and that we have one point that had a pretty large and different Cook distance. Given that this is a very unbalanced data set, that is that there is very unequal number of data points for the combinations of all explanatory variables in the book, but not here in the video. The final model LISA 3 was refitted without this point, and we did indeed found differences in the parameter values when the model was fitted with all the data and without this point that happened to have a very large Cook distance. So the conclusions that we are going to convey need to be tempered by the fact that this is a very unbalanced data set. We could obtain the parameter estimates and produce a table and a plot, but this is at least to me very hard as a way of conveying the meaning of the parameters. It is better and simpler, at least to me, to produce the conditional plots, and the conditional plots obtained with the GGFX. We see the differences, the predicted average frequencies for the different combinations of all the explanatory variables, and this is a lot more meaningful as a way of explanations of the implied parameter estimates. The Bayesian model fitting, I'm going to make some cheating here, in that I did not carry out, neither in the book nor here in the video, the Bayesian model selection. This should be done using the LU package, as was done in previous videos. So I'm going to start with the statement that the response variables has a negative binomial distribution, and this negative binomial distribution with the parameter mu and the parameter phi, which I forgot to put, and the log-link function. So I'm going to include here all single effects and all pairwise interactions for this model. I'm going to use the command get prior of the package BRMS to notice the priors that need to be defined in the log scale. So the priors I'm going to use is I'm going to define priors for the intercept. The intercept is the log of the mean of the response variable for the reference values of the explanatory variables, categorical explanatory variables, and I'm going to use a prior of with a normal distribution of 0 and a standard deviation of 1, meaning that 95% of the values of all the coefficients in class B, all these coefficients, are expected to be between minus 1.96, minus 2 2.96 and plus 2.96, and that I use a gamma distribution for the class shape. This prior was discussed in the videos of the previous chapter, and I'm not going to reiterate it here. So here are the implied values of the coefficients for the intercept in the log-link scale, for the partial slope again in the log-link scale, and for the phi or dispersion parameter of the negative binomial distribution. So the fitted model, here is the formula, the family indicated, the priors that we just defined, and the usual commands indicating the parallelization of the calculations, the number of chains, the number of iterations, and some extra parameters suggested by a previous fit of the model. Here are the marginal posterior distributions of the model parameters in the log-link scale, and the metrics of the convergence of the Hamiltonian Monte Carlo algorithm. What we see here is that the R hats are all close to 1 as a sign that the chains have converged to a common posterior distribution, and that we have pretty large number of independent sample estimates in each of the chains for all the parameters. Here are the parameters for the for the mean. Here are the parameters affecting the mean of the response variable, and here is the parameter of the shape coefficient, shape parameter. Here is the posterior distribution of the shape coefficient of the negative binomial distribution. The interpretations of these parameters can be done in the same way that we did for the frequentist model fitting, and for the sake of brevity I'm not going to repeat it here. So instead of using the point maximum likelihood estimate obtained in the frequentist fitting, you could replace it with the mean of the posterior distribution of each of these parameters. The posterior distribution for all parameters converge for the three chains converge to a common posterior distribution as suggested by the R hat coefficients. This model explains 91.4% of the variation of the response variable, which is extremely good. The goodness of fit of the model to the data can be assessed using the Donald-Smith residuals obtained from the posterior predicted distribution using the package Dharma. Again, this is the posterior predicted distribution. This posterior predicted distribution is using the command create Dharma of this package with additional input that includes the observed value and the defeated response, and these resulting Donald-Smith residuals are converted to a normal distribution, and they will have a normal distribution, I stress it again, only when the model fits well. So we create also a data frame in order to make the plots for the residual analysis. This will have these coefficients, these residuals, the explanatory variables, the fitted parameters, and the Pareto K coefficients. There is also a discussion about how to estimate the index of overdispersion for Bayesian GLMs. This is a little bit involved, not difficult, just involved, and for the sake of brevity I omit it from the video, but please see details in the book if you're interested in that. So the plots show us that the following: the plots of the residuals against the fitted value is not very satisfactory. So even disregarding the right hand side that shows because it has only 3 points, we see a little bit of a triangular shape here, which suggests that the variation of the residuals is large for small fitted values, small predicted values, and it decreases for larger values of the fitted values of the response variable. So this triangular shape is by no means satisfactory and suggests that the model could be improved. So here in the next three plots, B, C, and D, showing the combinations of explanatory levels of categorical explanatory variables, we by and large see that the median of the residuals is not too dissimilar from zero, and that often, but not always, the variation, the width of the boxes indicating the variation of the residuals is not too dissimilar for some of the combinations, but perhaps for others, yes. This is also can also be seen here in the plot of the time of the day and sun. So the variation of some of the residuals is pretty small. The variation of some of the residual for some other combinations of explanatory variables is pretty large. So these Donald-Smith residuals, transformed Donald-Smith residuals, do indeed have a normal distribution, and what we see here in the Pareto K coefficients is that many points are in the very good range, but there are a significant amount of points here in the only good part. This does not mean that we need to assess the sensitivity of the model to all these points. It means that we should be very cautionary when interpret the coefficients, when interpret the result of this Bayesian GLM, due to this plot of the Bayesian of the Pareto K coefficients and this heterogeneity of the variation of the residuals in the A plot of this graph. So in the conditional curves, we obtain a large number of conditional points or conditional curves. Simply, I called different levels of the different conditional points by simply replacing here in this is a list, by replacing different numbers. So I would put the 1, 2, 3, 4, 5, the number 6. If I wanted to obtain this point, I would introduce the number 6 here, and likewise for all the rest. This is a lot more interesting to see as in order to interpret the implications of the fitted Bayesian model to this data. We could obtain, and this is to me at least not a highly relevant, we can obtain the mean of the marginal posterior distributions and their 95% credible intervals in pale blue in the left hand side plot, and here we have the distributions of all the parameters affected the mean of the response variable for this model with the 95% credible intervals. So this concludes the video in which I show the relationship between count GLMs and the old-fashioned log linear analysis, in which we always start with exploratory data analysis, frequentist model fitting involving a large exercise in model selection, and the Bayesian model fitting. All codes and data can be found in this website, and I hope you found this video interesting, and I thank you for your attention.